All right, for those of you that are sticking around, I'm just briefly going to introduce some of the other the information that is vital to understanding what we're doing here in these labs. So we're talking about weather variability as well as climate change. And so first and foremost, it is always important to remember and to note that weather and climate are two different things. Weather is the short-term state of the atmosphere, so weather can change from day to day, it can change from hour to hour. The difference between weather and climate is that climate is only measured over a long time period. So it's going to show us long-term patterns. It's going to take averages of weather, which happen quickly in succession. And so climate is going to be the total amount of weather averaged over longer periods of time. So keeping that in mind, that is a very important and clear distinction that needs to be made when discussing weather versus climate. We've also had some labs dealing with climate types, and this is going to also impact not only exercise 24, but also exercise 26 when we talk about different climate classifications, again, using the Köppen climate classification system. That's something that you've been familiar with. But depending on the climate, that's also going to impact the biosphere, or the type of plants and animals, the flora and fauna that may or may not exist or thrive in certain areas around the world based off of their climates. And so one major component when we do talk about climate is climate change. There is a ton of evidence that shows us that more or less since the Industrial Revolution, that's in the 1800s, due to anthropogenic activity, anthropogenic meaning human activity, that there has been a large increase in greenhouse gases, specifically carbon dioxide. That's one of the easiest ones that we use to measure the amount of greenhouse gases that have been released into the atmosphere starting around the Industrial Revolution, around the 1800s, when we really started burning coal and other fuels to power our growing way of life. We needed more energy. And so this is where climate change from an anthropogenic perspective really started to come into its own. And so with increased greenhouse gases emitted into the atmosphere, again, carbon dioxide is what we often reference because it's an easy one to measure, and that is also what your figures in your practicing graded labs are going to be looking at. With an increase in greenhouse gases, we are seeing trends that there are greater increases or more extreme weather events. So whether that means more droughts here in California, more forest fires, again, that can come as a result of a drought. We're seeing that not only in the United States, not only here on the West Coast, but Australia over the last 2, 3, 4 years has also had really intense wildfire seasons. But not only that, we are also witnessing more extreme storms, things like hurricanes. And so there's plenty of evidence showing that hurricanes are happening more frequently and that they are more extreme. And so these are just a quick overview, simplified examples of how climate is changing. Scientists largely agree that it is impacted by anthropogenic activities and really how it is making natural disasters more frequent and more extreme. And this is linked back to, again, the emission of greenhouse gases, specifically carbon dioxide. And so that, again, is the information that we're really talking about when we measure climate change and we talk about measuring climate change over long periods of time. There are obviously many things that we can consider. And so these individual figures are showing various global temperature changes and trends of how it was warmer and it's getting colder. And again, this is a time period over millions of years. And so we can see from our best calculations and our best estimates that overall there has been a cooling over the last 70 million years. But when we dive into more specific details, right? So from 70 million years, we are now looking at the last 150,000 years to present. We can see that there are more extreme temperature fluctuations, temperature changes. And when we break that down into the last 1,000 years, we can see that there has been an acute trend of warming that is taking place. And so really this is what we are looking at, and this is what you are going to be reading about throughout the lecture content. You'll notice in the supplemental reading that it does mention the greenhouse gas concentrations and how that gets measured over time, again, specifically looking at CO2. In addition to that, this is the determining climates of the past, where we use specific oxygen isotopes, and we can analyze basically the molecular weight of oxygen. And so again, there's additional information in the supplemental reading, but the short and sweet component of this is that there are lighter oxygen isotopes, 16O versus 18O. We can see that 16O, because it is lighter, it is easier to evaporate. And so when that oxygen isotope, again, a part of water, H2O, rains and freezes in ice, there's a larger component of oxygen, the 16 isotope oxygen, that gets evaporated and frozen into ice. Because the 18 oxygen is just a little bit heavier, again on a molecular level, there's going to be a higher concentration of 18 oxygen left over in the oceans. And so we can actually calculate the amount of, or the difference between how much of this 16O isotope is within the water or out and frozen. And so when the 16O is returned back to the ocean, and there are more of these normal amounts between 16 and 18O located in the ocean, but we can see this change in a glacial period where we have a lot of glaciers, meaning that it has become very cold, versus the interglacial regions when it is warmer. And so depending on the concentration of 16 isotopes oxygen versus the 18 oxygen, that helps us to determine the global climate temperatures, as well as how climate has been changing over, again, thousands and millions of years. And one way that we measure this, or are able to measure this, is through ice cores. And this is, again, how we can manage and analyze the oxygen isotopes, because there are air bubbles trapped within those ice cores. And so that's also going to give us that ratio of 18O to 16O, where we can see the variation of the changes in the concentration. And that is going to help us, again, through those tiny air bubbles, be able to analyze what the concentration of oxygen, as well as the concentration of carbon dioxide and other gases and other particulates existed or exist in those ice cores. And the reason that we use ice cores is because over thousands or millions of years, you're going to have a buildup of ice sheets. The glaciers are going to continue to grow. And by drilling down into that, we are almost literally drilling into the past. And so we can collect air bubbles that had frozen in those glaciers from thousands and millions of years ago. And that's how they're able to extract ancient air. And so these trends as a whole is really what helps us to understand the changes in climate. And not only that, but through things like ice cores, we are able to see how the concentrations of carbon dioxide, in addition to those oxygen isotopes, has been changing and continues to change. And so using Antarctica, and we use that ice cap that exists in Antarctica, and so we are able to date back to over 800,000 years of data from these ice cores. And what we've found through these ice cores is that there is a strong correlation between the change in global temperatures and the changes in the amount of greenhouse gases. So simply put, the more carbon dioxide that we are finding in these ice cores means that we are also finding there are warmer global temperatures. And so we can use that data, and we're seeing that again today, that the increase in temperature closely follows the increase in greenhouse gases. Again, in this figure down here, and this is the one that you're going to find in your supplemental reading, and the one that you'll be referencing throughout your labs, is showing exactly that. The carbon dioxide in relation to the Antarctic temperatures. And so you can see by these graphs, again, that as the increase in carbon dioxide exists, there tends to be an increase in Antarctic temperatures. So this is the overview of the information. I hope you find this interesting. I think it's pretty interesting how we're able to use those ice cores. We can basically drill into the past and analyze those air bubbles from thousands, almost a million years ago, so that we can see the different concentration in carbon dioxide, as well as using oxygen isotopes to more or less see whether we've gone through a period of glaciation or interglaciation. This is all, I believe, incredibly interesting stuff. So if you do have any additional questions about any of the content, please feel free to reach out to me. I also want to point out that you absolutely must read through the urban heat island effect. That can be found at the bottom of page 167 in your lab manual. You will definitely need to keep that in mind when answering one of those questions on the graded lab. So let me know if you have any questions. Otherwise, good luck.